Hello, math humans. We're going to do 9.7 today. We're going to be reviewing basic probabilities. So that would be like the probability of an event. And then we are going to talk about the probability of and. So the probability of A and B. And then the probability of or, like the probability of A or B. So today has a lot of definitions and wordy problems. So I've pre-written most of them out just so we can save a little bit of time. So we have some definitions. An experiment is an event for which the outcome is uncertain. So in theory, when we do statistics, we're not sure how an experiment is going to turn out, which is why the outcome is uncertain. So if I'm pulling marbles from a bag, I'm not sure what marble I'm going to get when I pull it out of the bag. Outcomes are the possible results. So maybe I can get a blue marble or a red marble or a green marble. Those could potentially be my outcomes. The sample space is the set of all possible outcomes of an experiment. So how many things could potentially happen? An event is maybe I want to know what's the probability of getting a red marble out of a mixed bag of marbles. And then my basic probability is always the probability of how many potential events are there out of the entire sample space. So for example, how many red marbles are there? So that would be your event divided by the total number of marbles in a bag. Okay, so that would be our basic probability. All right. Just some numbers for probabilities. If you get that the probability is 0, that means that that event is either impossible or improbable, okay? If you get a probability of 0.5 or 1/2, that means that it's equally likely to occur or equally likely to not occur. And then if you were to get a probability of 1.0, that's a probability of 100%. So it is guaranteed to happen. Alrighty, so now we're going to start doing some examples as I figure out what to do with all my papers. Okay, so the first example says 2 coins are tossed. Alrighty, and then what is the probability that both coins end up heads up? When I toss coins, I could get a heads and a heads and a tails and a tails, or a tail and a head. So then my probability that they are both heads up, okay, so the total number is there are 4 possible outcomes and there's only one where they're both heads, so the probability is going to be 1 out of 4. Remembering that this is my total of the possibilities. And this would be how many of my events actually happen, okay? So the second example says a card is drawn from a standard deck of playing cards, which are 52 cards, in case you didn't know that. What's the probability that you draw an ace? So I've given you some generic card information if you're not a card-playing human. There are 4 suits of cards. There are hearts, spades, diamonds, and clubs. 2 of those suits are red. Diamonds and hearts are red, and then spades and clubs are black. The numbers in a deck of cards go from 2 to 10, and then the face cards are going to be Jack, Queen, King, and then ace is kind of an anomaly in, do I know how to spell that word? That's not right. We'll pretend I spelled it right. So it's an anomaly. Aces can be high or aces can be low, meaning that if an ace is high, I go Jack, King, Queen, ace, or I can play aces low and I would go ace, 2, 3. So an ace can either be above a king or an ace can be low. So the question says, what's the probability that you draw an ace? So we're looking for the probability of an ace. Well, the total number of events are 52, and there's an ace in each suit. So there would be 4 potential aces. In probabilities, you always need to reduce your fractions. Remember that the math frac button on your calculator is glorious because that means you don't have to simplify the fractions by hand, but you always want to make sure that you report in fraction form. There is no need to get a decimal, because this is actually kind of entertaining. That says I have a 1 in 13 chance of potentially getting an A. All right, as we move on to our next example, example number 3 is going to talk about playing the lottery in Arizona. So the pick game, a player chooses 6 different numbers from 1 to 44. If these 6 numbers match the 6 numbers that are chosen in any order is not specific, by the Lottery Commission, then the player wins the top prize. What is the probability of winning the prize if one ticket is purchased? And you can't see me smirking because I think this is really entertaining. So this actually combines combinations and probability. So the combination means how many different ways can I arrange those numbers. So there are 44 numbers, and I'm going to choose 6 of those numbers. So this is going to be my sample space, which I think is kind of entertaining. And just so you know, there are 7,059,052 different ways that you can organize the numbers 1 to 44 and choose 6 of those numbers at random. Okay? So this is not very encouraging, so then the probability of winning is going to equal, I'm going to get 1, because there's one winning combination out of the 7,059,052. Sometimes it's fun to buy a lottery ticket just because we like to see what happens. The chances of winning, 1 in 7 million, not very high. Okay? All right. The next definitions that we have are mutually exclusive. So it's kind of a weird set of words, but mutually exclusive means that events cannot happen at the same time. Exclusive means they're going to not happen at the same time. So then not mutually exclusive means that events can happen at the same time because they're not exclusive. And then we're going to talk about probabilities. So if 2 events are mutually exclusive, meaning they cannot happen at the same time, then the probability of A or B is going to equal the probability of A plus the probability of B. Okay? If, on the other hand, I have a not mutually exclusive event, meaning that things can happen at the same time, and our next example is going to illustrate this, then the probability of OR is the probability of A plus B minus the probability of and I like to think about this, this is where the 2 probabilities overlap. Okay? So if events cannot happen at the same time, then it's the probability of A added to the probability of B. But if they can happen at the same time, we have to take away where they overlap. Otherwise, we will have overdone our probability. So for our next example, example number 4, okay? All right. So we have one card being selected from a standard deck of 52 cards. So it says, what is the probability that the card is either a heart or a face card? Okay, so these events are not mutually exclusive because I can have a heart that is a face card. So these events are not mutually exclusive. Okay, so it's going to be the probability of a heart or a face is going to equal the probability of getting a heart plus the probability of getting a face minus the probability of a heart and a face. Okay, so pardon my shorthand notation. So let's talk about the probability of a heart. Okay, so the probability of hearts, there are 13 hearts in a deck of cards. So there's the probability of a heart. And I'm not going to reduce my fractions because I'm going to be adding and subtracting fractions. So I am just going to leave it like this for the time being. The probability of a face card, and remember a face is a jack, queen, or a king. The jokers don't count. So a jack, queen, king, and there are 3 per suit. There are 4 suits, so there are 12 out of 52. Okay? All right, and then the probability of both of these, so there are going to be 3 face cards that are hearts. So my probability of heart or face is going to equal 13 over 52 plus 12 over 52 minus the overlap, 3 over 52, okay? Alrighty, and so then my probability of heart or face is actually going to be 25 minus 3 is 22 over 52, and that reduces to 11 out of 26. So that would be my probability. So not quite half. So half would be 13 out of 26, so you have almost a 50% chance of getting that information correct. The next definition that we want to talk about are independent events. Okay, and statistics has lots of vocabulary, which is one of the things that makes it a little bit different than a standard math course. Independent events are independent if the outcome of one has no effect on the outcome of another. So I don't know that I can think of an example, but let's talk about what that means for the probability of and. If the events are independent, meaning that they have no effect on the outcome of another, then the probability of and is equal to the probability of A times the probability of B. Okay? Some other symbols that you will see when you talk about math, these are Venn diagram symbols. And remember that a Venn diagram is when we have circles, and maybe this represents sample space A, and this represents sample space B, and then I run those two sample spaces together. This area in here would be the overlapped area, okay? That would be the intersection right here. That would be the probability of and, meaning that it's the probability of something being in both categories. Alrighty, so the next example that we're going to do is a probability problem using a dice. And dice problems get to be a little bit entertaining because you may or may not choose to draw a dice diagram. I do because I think sometimes the probabilities with die get a little bit weird trying to decide if the events are independent or not independent, and so I just draw a dice chart. So in this particular problem, we're going to roll a standard die. So remember that a standard die is 6 sides, right? And then the numbers would be 1 to 6. Okay, they make all kinds of creative die, but for right now we're going to use a plain 6-sided die. And what is the probability that the sum is odd and key phrase? So if the events are not independent, that means that when I do the probability, I have to take away the probability of the overlap. Alrighty? So let's do this one. This one says, what's the probability that the sum is odd and greater? So let's just manage our dice chart, okay? So the probability of odd is going to be 3 and then the 5s and then the 7s because 7 is odd. Okay. 9s are odd and 11s are odd. Okay. The next thing that we're going to do is we're going to look at those numbers where the sum is greater than 7. So that would be 9, 10, sorry, not a 10. That would be these guys. Okay, so with a dice chart, it's easy to see where something satisfies both conditions. So we are looking for the probability of odd and that the sum is greater than 7. You'll notice that there are 6 times 6, there are 36 possible outcomes. So the probability is going to equal, there's my outcomes in the denominator, and I have 1, 2, 3, 4, 5, 6. There are 6 outcomes where the sum is odd and greater than 7, which is 1 out of 6. Okay? I have another couple of examples for us. So example number 6 says I'm going to have 2 die, and then I want the probability that the sum is odd or prime. Okay, so what is the probability that the sum is odd or prime? So I'm actually going to use the dice chart that we've already managed and bring in a highlighter. So the turquoise ones are our odd sums. Well, then we have to think about the prime numbers, okay? So the number of, I'm going to do the probability, or sorry, I'm going to do that the sum is odd, and that's going to be that probability that there are 18 of those guys that are odd. So now let's talk about the primes. So the thing that you have to remember is 2 is also prime, because by definition a prime number is itself and 1. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the probability that they are prime is going to be 15 out of 36. Okay, the overlap is going to be 14 out of 36 because they overlapped on all of the numbers except the 2. So the 2 was the only one that we had that wasn't considered. So the probability that the sum is odd, let me move it up so you can actually see it, that the probability is odd or prime is going to equal 18 over 36 plus 15 over 36 minus the overlap, 14 out of 36, and I get 19 out of 36. So there is my probability. We have one more little section to talk about, and that's the subject of complement, PLE. So we're not talking about a complement, ooh, you look so nice today. We're not doing that. We're talking about a mass complement. So let's say the probability of A is equal to a number, okay? Then the probability of not A, which would be the complement, so the complement is the opposite probability, is going to be the probability of the complement, and I'll put the complement of A, then that's going to be 1 minus the probability of A. So the probability that something happens is a number. The probability of the complement is 1 minus that number. Okay? So for your last example, example number 7, so let's say the probability of rain is going to be 40%. Then the probability of no rain is going to be 1 minus the 0.40, which is 0.60. So I know it seems a little bit intuitive that that's a true statement, but sometimes they will trick you and ask you this question. So the probability of no rain is going to be equal to 60% if we follow the same format. Alrighty, that is it for today. We are done with Chapter 9. Yeehaw! See you soon.